Let's look at how to compute sample sizes necessary to keep our confidence intervals within a certain margin of error. So on the left-hand side, we have the two formulas for calculating a confidence interval when we have proportions, and then when we have means, right? We're trying to do a population mean, and we don't know the standard deviation of the population. That's why we're using the t and the s instead of a z and a sigma. Okay, and then these two top formulas are the ones that give us the sample size necessary to do when we're doing population proportions. And then this one is the sample size necessary when we're doing z's, because we do know the standard deviation of our population. So this one's kind of, it's in the book, but we don't really use this one. Instead, we use it with a t and an s. And you can see that it's going to be the same formula, just with those different letters. That's why I included it here. Okay, where do these formulas come from? They really just come from the algebra of solving for these. So let's take the first one. E equals z, right? Square root of p hat q hat over n. And we want to solve for n. So that means we need to get n out of this fraction. And in order to get it out of the fraction, we have to square both sides. So that gives us e squared equals z squared. I'm just not putting the alpha over 2. It's just the same z, right? And then p hat q hat over n. We've now gotten rid of the square root. Now, to get n out of the fraction, we multiply both sides by n, and we have n e squared equals z squared p hat q hat. All right, and then to get n all by itself, we just divide both sides by e squared. That cancels out, and there is our n, right? There's that formula. Okay, so what about this formula? Where does this one come from? Why is there a 0.25 instead of a PQ? Well, if you haven't sampled yet, how do you know what the p hat is going to be, right? Because the p hat is your sample proportion. The whole point of doing this is we're trying to figure out how big our sample has to be in order to keep our margin of error, our E, within a certain size. And part of that calculation of figuring out what n has to be involves E. Well, that's easy because we set E. We say we want our margin of error to be within 1%. Then E becomes 0.01. The z squared, the z alpha thing, well, that just comes from how confident we want to be, right? If we want to be 95% or 90% or whatever our confidence level is going to be, we go and get our z from our tables or technology. So those we can calculate and know without knowing anything about our sample. But P and Q, P hat and Q hat, those come from our sample. We have to now actually go out and grab a sample and then count up how many people have whatever characteristic it is we're testing, and then that do a proportion, and that gives us P hat, and then 1 minus it gives us Q hat. So it's kind of silly to have them as part of our formula when we're supposed to be doing this before we actually do our sample, because how do we know what P hat and Q hat would be? So either we've already done the experiment before, and we can use that result for our guesstimated p hat and q hat, or we can use the more conservative estimate of, well, you know what, we don't know what p hat and q hat are going to be, so let's just let them be 0.5 and 0.5. 50% each. There's an even split of our p's and q's, and then p hat times q hat becomes 0.25. And the reason why we use that is because that makes n as big as possible, right? Because n gets bigger if the number on top gets bigger. And the biggest p times q will ever be is 1/2 times 1/2, which gives us 1/4, 0.25. If you let p get bigger than 0.5, then q gets smaller than 0.5, and when you multiply those two together, this number actually gets smaller. So by using 0.25, we've basically hedged our bets. No matter what size p hat is, the n that we get will now be good enough to keep our E within whatever size we want to keep it. Which also brings us to the idea of this isn't really a strictly equal, right? It's going to be a greater than or equal. So remember, with these types of questions, we're trying to figure out the minimum sample size, right? How big does our sample have to be to keep our margin of error within a certain amount? And if you look at these formulas, or if you look at them from their original standpoint, right, we're trying to keep E at, let's say, 2% or smaller. Well, as n gets bigger and bigger and bigger, this number, this whole thing right on the right side, i.e. E, gets smaller and smaller and smaller. So that's why when we're solving for n, it's a minimum sample size, because if n is actually bigger than that, then E is just going to end up being smaller than what we wanted, right? If we set it at 1% and we make n bigger than what the formula tells us, then E is just going to be even smaller than 1%. Okay, well, when you run the numbers, when you actually put in 1% here and you go and get your Z from your table or whatever, and then you put in P and Q, or you use the 0.25, whatever, do you really think you're going to get a whole number? No, you're almost guaranteed not to get a whole number. But n is the number of people sampled, right, or the sample size. Even if you're sampling things instead of people, it still has to be a whole number. You can't sample 0.3 of something. So this brings up the point of, well, what happens when this number is a decimal, which it almost always will be? You always round up. Even if you run the numbers and n comes out to be, let's say, 100.001. Well, that means in order to keep your margin of error at the 1% that you set this at, you would have to sample 100.001 people. And if you sample anything less than that, your margin of error will actually be bigger than 1%. So if you actually rounded that down to 100 and sampled 100 people, your margin of error, your E, is going to be slightly bigger than 1%. So in order to make it 1% or smaller, you always round up. And that 100.001 would round up to 101, and you would go out and sample 101 people. Okay, so I know that's kind of confusing in the beginning, but if you think about it, it makes sense. So whatever number you're getting for n, whatever the decimal number is, you always round up to the next biggest integer, because you're trying to keep E, your margin of error, at a certain level or smaller. So you're solving for a minimum n, and when that minimum n comes out to be a decimal, then you have to round up, because it's a minimum, right? You round up, and that next largest integer n is your actual number that you're doing. All right, we could do the same algebra for this one, and we could get the same formula here. I'm not going to waste time with that. Instead, let's look at how we can do this with technology. You may have already noticed when we were doing some of these things. Let's start with the proportional one, right? So if we go to proportional statistics, one sample, look at this, our third option, is sample size. If you click on that, it's going to bring up this odd looking thing. Its default is a hypothesis test power, but we're not doing that. We're doing confidence interval widths. Okay, here your required parameters. This is where you need to tell it what things are. So you set your confidence level. You want to be 95% confident or whatever, right? That dictates what your z of alpha over 2 is. You set your target proportion. That's your p hat. If you know what your p hat is, then you put that in here, but if you don't, you just put in 0.5, and then that gives you the 0.25, right, version of p hat times q hat. And then over here it says enter 1. So if I give it a width, it's going to give me a sample size. But here's where you have to be careful. If you want your E to be 1%, you don't put 0.01, you put 0.02, because width, the way StatCrunch thinks of width, is it needs to be the total width of your interval. So it's, remember, your interval is 2 times E, because your interval goes from p hat minus E to p hat plus E, and so you get a 2E width. So that's the next place where you can have some problems. And so it looks like you need 9604, but actually according to this, 9604 gives you a width of a little less than 2, right? See, because to make it exactly 2 would have been like 96.03 point 9603 point like 9 or something, which is impossible. So it rounded it up, which made your width a little bit smaller than 2%, which means your E is a little bit less than 1%. But in order to keep your E at a maximum of 1%, you need to sample 9,604 people. That's how it works. It's very simple. You can do the same thing for the T, right? If we're doing T statistics with one sample, there's my power sample size. Again, it defaults to hypothesis, but if we're doing confidence intervals, we click on that. Here's the same required parameters where we have to give it the confidence level that we're testing at, the standard deviation, so that's where you would put in your S, right? And then the width is just like before. If you want to keep your E to be so much, and remember now that we're dealing with means, our E is no longer between 0 and 1, right? Because when we're dealing with proportions, our E is a proportional type of thing. Now, if we're dealing with feet, then this is a standard deviation, and then our E is in terms of feet and that kind of thing. So you can have numbers bigger than 1. But the width is going to be 2 times whatever your E is. So if you want to keep your E to plus and minus 2 feet, then you'd have to make the width 4. And then it says a sample size of 4 would keep the width down to 3 point something, right? And then if you wanted your E to be, let's say, 10, then you could do 20, and you only need that many, right? But if you wanted your E to be really small, like only 1, so that means half each, right? So your E is a half, your width is 1, then now all of a sudden you need 18, and that's how that works. So it's very simple, guys. It's easy to do in technology. It's pretty easy to do with the formulas as well. You're just plugging in, right? Look this up in a table or get it from technology. Same thing with your T. Look it up in a table, get it from technology. Plug in your S, plug in the E. For these, your E is just the number, right? For these, it's the decimal. If it wants to be 2%, then it's 0.02. And then run the math. Square it, you're done, right? Square each piece, blah, blah, blah. Very simple stuff. Just pay attention to the details, right? When you're in technology, width means 2 times E. When you're using formulas, E is just E. All right, and that should hopefully help you guys tackle some of these sample size questions.